absolute value functions. You might remember, I've told some of you as you've kind of worked through the functions review stuff that we did earlier, where they had you do the function translations and reflections and all that stuff. People had some trouble with that, understandably. This is, if you're still not feeling 100% in charge of that, you don't feel like you have that totally down, this is a great way to get it figured out. Absolute value functions, I mean, they're important in their own right. It's a function that you need to know about. It's something that it'll come up, again and again. But probably most importantly, they're a good example function. So we're going to do stuff with absolute value functions here that we'll repeat later in the year for harder functions. But it works the same way. So if you can understand how to graph absolute value functions, how to write a function from a graph, then that's going to help a great deal when we get into the harder stuff, like in chapter 5 with parabolas and quadratic functions. If you know this well, that makes that a ton easier. And one of the things we're going to do is we're going to tweak absolute value functions by sliding them around in the plane and stretching them or squashing them and reflecting them and doing all that stuff. Okay, so anyway, so what are they? Well, let's take a quick look here. Let's talk about absolute value functions as piecewise functions. And this is I'm not going to spend a great deal of time having you on the assignment write out piecewise functions, but I want you to be able to make this connection. Okay, so what does that mean? Well, remember we talked about piecewise functions, and many of you are still working through that part of the unit, working on that assignment, and that's okay. It's due, I think, tomorrow night, so you're fine. A piecewise function, remember, is a function that represents more than one behavior. Okay, so we looked at skydiving and things like that. Well, an absolute value function sort of is that way too, if you think about it. Think what an absolute value function does. What's the absolute value of 5?
5.
What's the absolute value of 10?
10.
What's the absolute value of 11?
11.
Okay, so in other words, if I take the absolute value of positive numbers, an absolute value function does absolutely nothing, leaves it alone. Okay, but what's the absolute value of negative 3? What's the absolute value of negative 7?
7.
So if I take the absolute value of negative numbers, the absolute value function does what? Makes them positive. And the way you make a negative number positive, what's the easiest way to make a negative number positive? Well, I could, but that's going to be a little tricky. Is there anything I could multiply it by to make it positive?
1.
Negative. Negative 1, right? So if I take the negative of a negative number, isn't that positive? Right? Does that make sense? So an absolute value function then, if we input a negative number, it's going to take its opposite, which is positive, by multiplying by negative 1. That's what this says, isn't it? Now look at this part here. If x is greater than 0, now what's that mean? X is, what's our word for that? If x is greater than 0, we're saying x is positive. That's it. It's positive, right? It's greater than 0, it's positive. If it's greater than 0, the absolute value of x does nothing to x, leaves it alone, like we said. If the absolute value of x is less than 0, how do we describe that? X is negative. Then look what it does. Whatever's inside the absolute value function gets multiplied by negative 1 to make it positive, right? And then the in-between case is just where if x is actually equal to 0, what's the absolute value of 0? 0. Okay, so it really does behave like a piecewise function. And if you go on and do more stuff in math, which I sincerely hope you all do, this is one way that you'll treat, like when you get to calculus, you treat absolute value functions. You always just turn it into a piecewise function and then do your stuff. Okay? Hey. Okay, so moving on. The graph of an absolute value function. That's really what we're going to focus on. The graph of an absolute value function always looks like a V. That's the shape of an absolute value function graph. Different shapes have different functions, and throughout the year we'll look at a lot of different kinds of functions. Each of them has its own characteristic basic shape. Now it can get tweaked, but absolute value functions are always V's. In the same way that quadratic functions, parabolas, are always U's. They're U-shaped functions. These are V's. Now we're going to do some stuff to these V's, We could take the V and we could slide it around in the XY plane. We could stretch it vertically and make it tall and skinny. We could squash it vertically and make it kind of wide. We could reflect it over the x-axis and turn it upside down. We could do lots of things. But ultimately, it's just some V. Maybe it's tweaked a little bit, but it's just a V shape. So left side in this case is just, if it's the absolute value of x, it's just negative x. Like we said, right side is x. The anatomy of an absolute value function. We're going to call these the legs of the function. Okay? The two sides are we call them legs. The vertex is the point right here. That's the most important point on the function, is the vertex, because it's sort of the anchor point. If we wanted to graph an absolute value function, we're always, now listen, I don't want people talking right now. If you need to talk, I'm going to have you step out there and do it. Okay? The vertex is the most important point. If we're going to graph an absolute value function to V, the best way to do it is to start with the vertex and just graph the legs from there, sketch the legs from there. So the vertex is really key. Notice that it has symmetry. If we look at the symmetry of this thing, it's got this reflective symmetry. That's really nice. If I draw half of it, I get the other half for free because it's just the reflection around that vertical line. Now we call that the axis of symmetry, and all it is just a vertical line through the vertex. That's it. We love symmetry in math. This is just kind of a beginning example of that, but we love symmetry in math because it allows us to avoid work. We can oftentimes use symmetry to do problems that otherwise would require lots of algebra. Okay, and so it's really handy in math. We love it. We make use of it whenever we can. And there are different kinds of symmetry. The kind that we're most used to is this reflective symmetry or folding symmetry, or line symmetry we call it. We'll look at some other symmetries later. But for now, this is the kind of symmetry that a V has and an absolute value function has. And we'll take advantage of that today, you'll see. All right, so moving on. We're ready to do some work with this stuff then. So what we're going to do is we're always going to compare absolute value functions to this starting point. This is called vertex form. And like I said, this is a great example function because we're going to see something later on in the class, in the not too distant future. We're going to look at parabolas, U-shaped functions, and they're going to have that kind of form. Now that's in the future. I mean, you don't need to know that now, but you see the parallels there. They're almost the same. And the meanings of the A and the H and K that we're going to discuss are almost exactly the same for a parabola as they are for an absolute value function. So learning this now pays lots of dividends later. So this is vertex form. And here's what I mean by that. What we're going to do, here's how I kind of want you to think about this. It'll be very helpful. Think about this as compared and contrasted with a much simpler example, like just a plain old line. If I graph a line, y equals mx plus b. X and y are the variables, right? M and b are what we call parameters. And you can call it that if you want to, but that's kind of the mathematical word. Meaning they're the values that we can tweak to change the line. We can dial in values for m and b to create any possible line in the universe. If I take an infinite xy plane, any line on that plane I can build by just choosing the right value of m, the slope, and b, the y-intercept, right? And so by dialing those in, I specify a line. Same thing is going to be true for the v absolute value function, the v-shaped absolute value function. Only I need 3. It's a slightly more complicated function. It's not just straight. It's got a bend in it, right? It's a v-shaped thing, and so that adds a little complexity. And it turns out that we need 3 of these numbers instead of just 2. But by dialing in the values of a and h and k, we can quickly specify an absolute value function. And that's what I'm going to show you how to do. It's very simple. It's no harder than it is for a line. So let's look at that. All right, so first of all, we know that the vertex of the point of the V is always located at the point HK. So whatever the value of H is, whatever number that is, it corresponds to the X coordinate of the vertex, and whatever the number value of k is, it corresponds to the y-coordinate of the vertex. So it's really easy to find that vertex. All you gotta do is just figure out what those numbers are, okay? A, we know they're V-shaped. Now, there's a lot of stuff we could say about A, but don't bother, I mean, I'll say it, but then I'm gonna show you a much quicker and simpler way of thinking about what A means. If A is negative, the graph opens down. That's true. If A is positive, the graph opens up. If A is a small number, the V gets wider. If it's a big number, it gets narrower. It gets stretched out vertically. But all that stuff is summarized in this one simple red statement. A is the slope of the right side of the V, the right leg of the V. Its slope is always going to be A. And then the left slope is just, the left leg is just a mirror image of that, right? So if I want to start with a function, with an equation, and make a graph, it's really easy to do. All I do is I start with the vertex. I find the coordinates of the vertex, plot that on the xy plane. I'm going to use the slope, A, to get a second point on the right side. I'll just reflect that over the axis of symmetry to get the left point for free, and then just connect the dots to create the V. Okay, so like this, for example. Let's look at this example here. Now, let's compare this to vertex form, and you're going to have to memorize this, but you may not have it memorized yet. Well, let's see if you do. What is vertex form? Y equals A times x minus h, good, plus k. Okay, so we're just going to compare vertex form to this example. What we want to do is we want to figure out what are the values of a and h and k in this example. Okay. Another way of thinking about that, if I started with the red vertex form, what numbers could I plug in for a and h and k to get this example? So first of all, what's a? Negative 1. Everybody agree? Okay. A negative sign out front, that implies a negative 1. So a is negative 1. Now what about h and k? Because those are the coordinates of the vertex. K is easy. What's k? 3. K is easy. H is a little bit tricky. You have to be more careful with H. What's H?
2x.
Ah, what did I hear back here? It is negative 2. Yeah, how come it's negative 2? Okay, good, because H is the number that's being subtracted from X, right? And so if I have X plus 2 is equivalent to X minus what? Minus a negative, right? If you subtract a negative, it's the same as adding. Agreed? And so what you got to remember about this, that's the tricky one. It's real. Once you know the trick, though, it's not a big deal. You just have to remember it. So you know that whatever the sign is, the operation is that connects x to h. So if it's x plus h, the sign is the opposite. H would be negative. If I end up with an absolute value of like x minus 4, what would h be?
Positive 4.
Positive 4. If it's a negative, if it's a minus sign in between, then it's a positive value of h, right? It's always the opposite of the operation. Make sense? Okay, so once you know that trick, though, it's no big deal. Okay, so then we know that h in this case is negative 2. So all I've got to do then, it's so simple. If I want to create this graph, couldn't be easier. All I got to do is locate the vertex on the xy plane. Well, its coordinates are negative 2, 3. So I'm going back 2, up 3, right? So there's the vertex. What's the slope of the right side?
Negative 1.
Negative 1. And if I write that as a fraction, that's just what?
Negative 1.
Negative 1 over 1. Now remember, slope is rise over run. So if I start here, how much am I going to rise? Down 1. I rise by negative 1. So I'm going down 1 and over 1. There's my second point. There's the right leg of the V. So what's the left leg? Well, that's easy. I'll just, instead of going down 1 and right 1, I go down 1 and left 1. There it is. That's it. Okay, that's the V that goes with that absolute value function. Yeah, it's no big deal. So to summarize, this is what we did, right? We found the vertex, located that. We found the slope of the right side of the V to create another point on the right side. We reflected it over the axis of symmetry to get like the cousin point, the other one, the reflected point, and then just made a V. Right? So try this one. Get out your notebooks, or I have paper if you need paper, but try this one in your groups. See if you can come up with a quick sketch of that. All right, first of all, what are the values of A and H and K? So let's start with A. What's A?
-1,
Okay, what is the vertex HK?
1 and 1.
Okay, this is the tricky part. H is not -1, it's 1, right? Because 1 is the number that's being subtracted from X. So it's 1, 1. Okay, so then doesn't that mean that this is what the graph looks like?
Yep.
Right? Vertex is at 1, whoops. Oh, too far. Okay, it's that, right? Because look, our vertex then has coordinates 1, 1, and the slope is -1, so that means I'm dropping by 1, rising by -1, running by +1, right? And then so here's the right leg reflected over the axis of symmetry to get the left leg. Okay? Okay? Which part? Where the vertex is? Okay, the vertex, because remember that vertex form is A times the absolute value of X minus H plus K. So 1 must be H, right? 1 is K. So I go over 1, up 1 to get there. Okay? Right? And then the slope is -1. Okay, so A is the slope of the right side, so there's my starting point. -1, 1. Yep. Okay? That's it. You got it. Okay, so one more of those. Actually, no. Sorry. Okay, last part. Okay, so now we're going to turn the process around. The other thing I'm going to ask you to do. Okay, so the other thing I'm going to ask you to do is I'm going to give you a graph. I'm going to ask you to write down the absolute value function that goes with that graph. So here's the graph. I think this is easier myself. I mean, I don't know, it's 6 of one, half dozen of the other. They're both pretty easy once you get to have it. So by looking at this, and we say in math, just by inspecting the graph, what is the vertex? What are the coordinates of the vertex? 0, -3. I go over 0 and down 3, right? So HK must equal 0, -3, because that's that point right there, isn't it?
Yep.
Right? Now what about A? I'm going to look at the right side. I got to pick 2 convenient points to make a slope triangle, right? So there's 1. There's 1 maybe?
Yeah.
Okay. So then that means I'm going to rise by 2 and run by 1. So what's A? 2. 2 over 1, which is just 2, right? So A equals 2. And so if I put that all together then, we know that the form of an absolute value function is A times the absolute value of X minus H, right, plus K. So what do I get? Y equals
2 times the absolute value of X plus 0.
of X minus 0, right?
Minus 3.
Plus -3. You know, I can simplify that. I can write that in an easier way, and I want you to get the answer correct. It needs to be written simplified. So what is X minus 0? X, right? So I could rewrite this as 2 times the absolute value of X, and then plus -3 is just, there you go, right? Okay, so to summarize, this is what we got. Vertex is at 0, -3, so we know it's going to look like that. X minus 0 times X plus -3, X minus 3. A is, by just making a slope triangle, is +2. And so we can simplify that to 2 times the absolute value of x minus 3. Okay? Last one, we're out of here. Just see if we can just do this together real quick. So what are the coordinates of the vertex?
0 and 3.
Good. What's the slope of the right side? Okay, good. Up 1 over 2. Very good. So we go up 1 over 2. Right, so then A equals 1/2. So what is the absolute value function?
Y equals 1/2 times the absolute value of x
X.
plus 3.
Okay, good. It's x minus 0, which is just x, right? And then plus 3. Got it? Okay, 205.
Huh?